In particular, I would like to start by the second part of the title of this workshop, Multineutron Clusters in Nuclei and Stars. And in particular, from the extreme conditions of matter inside neutron stars. When we go from the surface towards the inner core of a neutron star, we find different density regimes. And in particular, when we get to the outer core, we have that the density inside neutron stars is actually very close to the nuclear saturation density, so the density that we have inside the nucleus. And so in this region here, the equation of state of nuclear matter is actually determined by the nuclear interaction. And so this connects, let's say, the infinitely big world of neutron stars to the macroscopic world of finite nuclei. And so to study the structure, composition, and dynamics of neutron stars, we need to solve general relativity equations that require as an input the nuclear matter equation of state. And this is modeled as you see here. So we look at the energy per nucleon as a function of the total density, so density of protons plus density of neutrons, and as a function of alpha. So this is an asymmetry parameter that takes into account the difference between density of neutrons and density of protons. In particular, the first term that contributes to the energy per nucleon is the case in which alpha is equal to 0, that you see here. So the equation of state of symmetric nuclear matter, density of neutrons equal to density of protons. But then we start to have also contributions from the asymmetry. And the density dependence of such a contribution is given by the symmetry energy. So the symmetry energy can be expanded, as you see here, around saturation density, and it is determined in this limit by two parameters. So J, symmetry energy at saturation density, and you can clearly see here, it is basically the difference at saturation density between the energy per nucleon of the extreme case, alpha equal to 1, so pure neutron matter and symmetric nuclear matter, and then the slope parameter. The importance of the slope parameter is very clear from the picture, because here you see that it is basically the slope of the equation of state of pure neutron matter at saturation density, and so it is directly related to the pressure of pure neutron matter at saturation density. And so J and L are important parameters determining the nuclear matter equation of state, and so we want to constrain them. And a way to do that is actually to look at quantities that can be measured in the lab. So one of them is the neutron skin thickness. The neutron skin thickness is the difference between the radius of the neutron distribution and the radius of the proton distribution inside the nucleus. So, okay. You see here a picture of showing like the neutron skin of lead-208 as a function of the slope parameter for different ab initio and energy density functional theory calculations. And you actually see, okay, there is something that went wrong, but in any case, the important thing is very clear. You see that there is a nice linear correlation between these two quantities. And so this suggests that a precise determination of the neutron skin of lead-208 can be translated into a constraint on the slope parameter. But there are also other ways that we can use in order to constrain the symmetry energy, other observables. And in particular, another one that I would like to focus on is the electric dipole polarizability. So the electric dipole polarizability measures the tendency of the nucleus to deform in an electromagnetic field. And so you see here a picture which is very similar to the one of the neutron skin, which connects the product between the polarizability and the symmetry energy at saturation density with the slope parameter for these two theoretical approaches. And also here we see a nice correlation coming out. And so via a synergy of experimental measurements of the polarizability and theoretical calculations, we can say something on the symmetry energy parameter starting from an electromagnetic observable, so the electric dipole polarizability. And in particular, as I am a theorist, I ask myself, okay, how can I calculate this? And you see here the definition of the dipole polarizability. Maybe you see it, so it's up there, but I don't see the, okay, here. So it is an inverse energy weighted integral of this object here, which is the so-called response function. This was something that was already introduced by Sauri before. It's an object that contains all the information regarding the behavior of the nucleus in the presence of an electromagnetic probe. In my case, I will focus in particular on electric dipole transitions, because we are interested in the electric dipole polarizability. And so in this specific case, we have that the response function looks like this as a function of the energy of the photon. So we will have that if the energy of the photon is low, the nucleus will be excited into excited bound states. But then when the nucleus, when the energy of the photon overcomes the nucleon separation energy, we enter the continuum spectrum, and so we can have pygmy dipole modes when we have a large neutron excess, and then at higher energies we have the giant dipole resonance, which is interpreted as collective motion of protons and neutrons inside the nucleus, and I will come back to this interpretation later in the talk. So at this point, we want to, let's say, have predictions of the dipole polarizability. For this, we need to calculate the response function. And to calculate the response function, we need to know the ground state properties of nuclei of the nucleus, as well as all the possible final states. I am very grateful to Sauri, Anna, and Gauta before me, because they introduced the way in which I would like to do this, which is ab initio nuclear theory. So combining chiral EFT interactions with systematically improvable many-body methods, and in particular, I will work with coupled cluster theory. However, as Sauri was pointing out, the problem of calculating the response function lies especially in the fact that it depends on the continuum spectrum of the nucleus. Sauri already pointed out that a way to deal with this is actually to look at integral quantities. So integral transforms of the response that allow us to basically reduce the continuum problem to a bound state-like problem. And if you would like to know more about this, just look at Miriam's poster tomorrow. So let us go to some first results. So here I'm focusing on closed shell nuclei first. So we are starting making a reference to Gauta's talk from a spherical reference state. These are results for calcium-40 and calcium-48. So you can see here the experimentalists measure the polarizability of calcium-40 as and you can see it here as represented as a in relation to the polarizability of calcium-48, which was previously measured. And in particular, in blue, you see the experimental results. The colored crosses are coupled cluster calculations with different interactions. And the ellipsoids here are instead energy density functional theory calculations employing different functionals. And there are two important things to notice here. We see that these two quantities show like a nice linear correlations for both theoretical approaches. And also, we have both chiral EFT interactions as well as energy density functionals with which we are able to reproduce both the polarizability of calcium-40 and the polarizability of calcium-48. And so we can think, okay, what are the constraints on the symmetry energy that we can get from these chiral EFT interactions and energy density functionals? And you can see them here. So in blue, we have the constraints coming from the chiral forces we used in this work. And then in red, the constraints from energy density functionals. And in particular, it is interesting to look at the comparison between the full red band and the etched red band. In this case, in fact, we see that there is in this case, in fact, we see that the ADFs which are fitted on the polarizability of lead-208 are indicating lower values of J and L, and they are also, let's say, shrinking somehow the constraint. We can also compare these constraints to available values in the literature. For example, we have here two ranges that come from a recent review by Jim Latimer. In particular, the first range comes from making like a global average of all the experimental measurements we have for the neutron skin of lead-208 and calcium-48. And then the second one instead comes just by considering the experimental results which come from parity violating elastic electron scattering experiments. And in this case, we see that it is the constraint is slightly larger. We can also compare with available nuclear matter calculations. For example, Drischler et al., where also a Bayesian uncertainty quantification was performed. I think Daniel is part of it. Then Wu et al., based on a set of non-implausible interactions. And the last constraint I report here is a non-parametric model of the EOS constrained by both chiral EFT and astrophysical observations. And we can see that in general, the constraints are kind of in agreement among each other. Okay, so happy ending for calcium-40 and calcium-48. And so here we have, okay, agreement with experiment, but if we look at the full, let's say, isotopic chain, we actually see that there is a lot that we don't know regarding how the polarizability evolves along this isotopic chain, but the experimentalists are performing new experiments, especially in open shell nuclei close to doubly magic nuclei. And also with future upgrades of facilities like RIC and FRIB, we could be able to perform Coulomb excitation measurements for very neutron-rich nuclei, which would be very useful to get more insight on constraints on the symmetry energy. So we need to extend our method beyond closed shell nuclei. And one way to do it, still sticking to a spherical reference state, we can test how much we can do with that, is to consider the case of nuclei in the vicinity of the closed shells, and in particular, two-particle attached systems, which are, let's say, the object of this experimental campaign. So two-particle attached system is just like a closed shell core plus two particles. And the main idea of this approach is that we are seeing states of these nuclei as excited states of the closed shell neighbor. So we will basically say that, okay, like the two-particle attached wave function is basically the action of an excitation operator on top of the closed shell wave function. And in particular, the excitation operator that we will choose will change the mass number. And so here we will have like, okay, I don't know. Okay, here. So here we will have like a first term, which is given by basically just adding two particles, so two particle zero hole excitations. And then we start with the usual particle hole expansion, and so we will have 2 particle 0 hole plus 1 particle 1 hole that gives us 3 particle 1 hole, etc. So at the moment, due to computational limitation, we are limited to this order here, and so we will see how far can we go with it. So we tested this approach first on alpha D along the oxygen isotopic chain. So for the oxygen isotopic chain, we have this experimental data in gray. We can perform the closed shell calculations in blue, the 2 particle attach calculations in green, and then in red we have available ab initio calculations in the literature performed using different methods and interactions. So the case of oxygen 16 and the oxygen 24 are particularly interesting because in this case we can perform both calculations, closed shell and 2 particle attached, and we obtain compatible results. And also in general we see that there is a very good agreement between experiment and theories, and so we can actually say that we have a good understanding of what's going on in terms of physics along this isotopic chain. Let us go to calcium. So in this case, I talked before about calcium 40 and calcium 48. There are other nuclei that we can tackle in the closed shell framework, so calcium 36 up to calcium 54. And then if we add the open shell results, we actually see that they are kind of lower with respect to the closed shell ones. And this can actually be interpreted as a many-body effect. In fact, what we noticed is that with the level of approximations at which we can use the 2 particle attach framework, so the maximum is 3 particle 1 hole, we are able to describe well low-lying states which have a simple 2 particle attach structures. And this is not the case when we actually go towards high excitation energy, and so we get more complex collective structures, and so we lose strength for this reason. But in general, let's say, despite the systematics, we see that the polarizability is increasing neutron number, and so this tells us that it is sensitive to the neutron to proton asymmetry. We can actually also go beyond that. I consider 2 particle attached system. We can also do the same with 2 particle removed systems. And in particular, we have here the case of calcium 38 and calcium 50 that provides us with a benchmark because they can be tackled from both sides as 2 particle attached and 2 particle removed systems, and we get compatible results. And with the 2 particle remove, we can also fill the gap in calcium 46. But unfortunately, we see that the many body effects are still quite important also in the case of 2 particle removed nuclei. One thing that would be really nice to have is experimental data, especially in this on the neutron-rich side of this plot. And just to see, let's say, what we can do right now to produce, let's say, synthetic data in order, while we wait for the actual experimental data, I just point you to Tim Eggert's poster. Okay. How much time do I have? Okay. So I talked up to now about the polarizability, but there are actually other nuclear properties which are particularly important for astrophysics. And in particular, if we think about the origin of elements beyond iron, we have that basically this is determined by the competition of 2 processes, beta decay and neutron capture rates along the nuclear chart while we go towards heavier elements. But when we get to heavier elements, another process that actually contributes to the abundance of the heaviest stable element is fission. And fission is a complex dynamical problem which is regulated by the time-dependent Schrödinger equation. This is, let's say, a very difficult problem, and in order, let's say, to train ourselves on the time-dependent Schrödinger equation, we can keep, let's say, fission as our long-term goal, and instead start to play with the time-dependent Schrödinger equation with a different physics case that we can handle better, which is the one of nuclear electromagnetic responses. I don't know what happened with my slides, but I will just say, okay, the show must go on. And, so the goal is actually to solve the time-dependent Schrödinger equation with an Hamiltonian that looks like this. So you have here H0 is the normal static nuclear Hamiltonian, plus a perturbation. This perturbation has strength epsilon. It is characterized by a time profile f of t, which is basically a pulse, a delta function that we model numerically as a Gaussian, that should be here. And it is multiplied by an operator that basically determines the nature of the perturbation, which is, in our case, we focus on the electric dipole operator. So basically, what we are doing is to give a Gaussian kick of dipole nature to our nucleus, and we see what happens during time evolution. And in time evolution, we consider, let's say, the expectation value of the dipole operator in time. We can perform a Fourier transform of it, and then we can relate directly this Fourier transform to the response function. So, and in order to do this, the fundamental object that we need is the solution of the time-dependent Schrödinger equation, and so the wave function. And to do that, we can actually extend the coupled cluster ansatz in order to include time dependence. And so we will have the exponential ansatz that we saw before, but our cluster operator, in this case, our cluster amplitudes will actually depend on time. And if we insert these ansatz into the time-dependent Schrödinger equation, we get the differential equations, which basically determine the art of our time evolution. Let us go and see some results. So, for example, here you see the time-dependent dipole for helium-4 and oxygen-16. We actually see that in both cases we have an oscillatory behavior, but let's say the modes, the oscillation modes that we see in the two nuclei are different. So we have, let's say, different energy modes in the end contributing. But then when we, let's say, go from, I really don't know what happened with my slides, when we go from the time-dependent dipole moment to the response function, we actually see that there is an important relation that we have to take into account. The one between the maximum simulation time and the resolution that we get at the level of the Fourier transform. And the two quantities are inversely proportional. So if I run my simulations up to 2000 Fermi over C, I will get a resolution which is around 0.6 MeV. But if I want a smaller resolution, I want to go to 0.3 MeV, I will have to run my simulation double. So I will have to get to 4000 Fermi over C. You have to think that for each time step, which is usually 1 Fermi over C, we have to solve the coupled cluster equations at least once. So this is actually pretty expensive. But in general, let's say, as you can see here, already with 2000 Fermi over C, we get, let's say, a reasonable description. So I started this talk just presenting how response functions can be calculated in a static way. So we can compare the results that we get considering response function in a time-dependent approach. So here you have the response in the time-dependent case, and here I'm comparing the time-dependent result to the static result in the case of sum rules. So you have m0, which is basically the integral of the response function, and the polarizability, which is and the polarizability. And so inverse energy weighted sum rule. And so in this case, we actually see, like I just showed in the time-dependent case, the build-up of the sum rule as a function of excitation energy. And we can see that when we get, let's say, to saturation, the two lines, the dashed dotted line and the solid line, are basically overlapped. We see deviations of less than 2% between these two approaches, which are completely independent between each other. And this is the case of helium-4, but we can do the same also for oxygen-16, and also in this case we get very good agreement. Okay, so it's nice sometimes to look at problems from a different perspective. However, if, I don't know, Nakamura-san asks me, okay, let's calculate the nuclear response function for a certain nucleus, I will actually use the static approach because it's way less expensive. So what is the advantage that we can get from a time-dependent calculation? So we have the wave function as a function of time. This means we have the densities, and we can look at how the density changes in time with respect to the ground state density. So here you see it for in the proton case, and here in blue for the neutron case. And we actually notice that the density fluctuates in opposite directions from protons and neutrons. And so this is the traditional view that people always had of the giant dipole resonance. So collective oscillations of protons against neutrons, and we are seeing this coming out from time-dependent ab initio calculations. Then another thing that we can actually do with a time-dependent framework is to consider values of epsilon, which up to now I kept small, which allow us to go beyond the so-called linear regime. So when we are in a linear perturbative regime, if I calculate the dipole moment, I don't know, for epsilon equal to 1 and epsilon equal to 10, I will get that the result for epsilon equal to 10 is 10 times the one for epsilon equal to 1. But actually, when this object here becomes of the order of nuclear excitation, so of the order of MeV, we will have that this is no longer true. And so nonlinearity effects are actually coming out. And so when actually this happens, so if we consider oxygen-16, we can look at a typical dipole transition strength, and we get, let's say, this value here, if we just do the square root. So we need something which is like epsilon equal to 100 MeV over Fermi to get a perturbation that goes up to MeV. And this is actually what happens. So you see here results for 10, 50, and 100 MeV, which are rescaled according to, let's say, the ratio between each other. If we were in the linear regime, these curves should be, let's say, all overlapped. However, we actually see that there are some deviations. And so this, let's say, is the non-linear behavior which starts to come out. What is this at the level of the spectrum of the nucleus? So this is a time-dependent DFT calculation for oxygen-16 as a function of epsilon star, of E star, which is basically equivalent to our epsilon. So large E star is equal to large epsilon. And so if we get to the largest value and we compare it with the solid line, we see that basically the giant dipole resonance is going towards lower energy. So we get some more strength at lower energies. In our case, we can try to do the same. We don't have much resolution because our differential equation problem becomes more stiffer when we consider high values of epsilon. However, you see, if you look at the green curve, you can actually see that the peak is coming down as here, and we have some more low energy strength. So qualitatively, we are actually seeing the same as in the mean field case. And with this, I got to the end of my talk. I would like to thank all my collaborators, and thank you for your attention.
Thank you very much, Francesca, for the nice talk. Questions? Carlos first.
Yes.
And then you get, again, the Japanese Express.
Bullet train.
So, when you talk about giant resonances, well, first of all, it looks to me that your slope parameter still is in the middle of many other calculations, so you cannot really make very final conclusions, except that if you... But for giant resonances, there are so much data, okay? And one of the problems with giant resonances is always the same. We can more or less explain the centroid, but the width with the microscopic calculations, they are kind of not really explaining the data. If you take lead, for example, and you try to do a microscopic RPA or QRPA or the best super RPA or whatever one has, it doesn't go well with the data. So it would be nice if you could also add to this scenario, showing that you can reproduce photo excitation of giant resonances, because this is something which is unresolved so far after 70 years of nuclear physics. Perhaps you guys, with Kepler-Coaster and microscopic calculations, can help us to solve this problem, which is there for a long time. I do not know. I'm just, I don't want to criticize your work. I just say that
Yes,
maybe
yes,
you can,
yes.
yeah,
No, like
very
in my case, I focused on some rules, so I haven't actually looked at the actual response function. I looked at that like in the time-dependent framework, but there we have like a dependence on this resolution. And also, like, since we are using like the R3-Fock basis and we are not evolving our orbitals, we are not able to actually calculate the width, as you say, at least in that framework for the moment, but that's something that we would like to do.
Yeah,
And
we've done a bit in the past, right? So we've tried oxygen-16 and calcium-40.
Yeah.
Calcium-40 comes out quite okay with respect to data. Oxygen-16, it's a bit fatter. So the thing is that with Francesca, she moved on to some rules because you could avoid inverting the response function. Now we are trying to revive this thing of the inversion, and Miriam is working on that. I think if we refine the tools there, maybe we can try to address this problem, but we probably don't go directly to lead.
It would be very nice if you could do that.
Yes, so we have Tobias first and then Takashi.
Francesca, thank you for the talk. It's more a curiosity. I mean, that I'm really puzzled with the helium-8, I mean, that peak for the B1. And then now you have alpha D for heavier nuclei. So this low energy problem doesn't came out in this heavier nuclei.
So maybe here we have to do some context.
Yes,
you are referring to helium-8, I imagine. The low energy peak in helium-8.
Yes.
Okay.
That doesn't. I mean, for heavy nuclei, this is not. It seems not relevant. I was wondering.
So
why?
in the case, for example, of calcium-40, calcium-48, our description of the discretized response function, which is in the end what then we use to calculate the polarizability, seems to be good enough to get to the experimental data. In that case, we have the same level of correlations that I actually used for helium-8, so up to triples. It might be that in the case of helium-8, due to the clustering structure of the system, we need to go beyond that, and that's what I was showing during the school, that if we compare our calculation to full CI, or like configuration interactions, in that case we get that there is like a 20% difference between our results at different, with the same interaction. So
just to complete, so
Yeah.
if you go to very rich neutron nuclei, maybe you could find the same disagreement. If you have a skin or
yeah, we
or
have
a
to
head.
see,
Okay.
we need the experimental data there.
Very nice talk. Thank you very much. In the beginning, you showed, I think page 4, you showed the correlation between alpha D and the J, or I think. And I had the impression that the, maybe page 4, I think. Yes. I had the impression left figure has a very good correlation, but on the other hand, right figure shows rather wide widths, especially if you include ab initio. So then the correlation seems to be a little bit broken. But what? Maybe you have some comments on this. You see
So,
this?
like in this case, okay, like with respect to energy density functional theory, like it looks like chiral EFT interactions are actually constraining the values of the polarizability up to a certain point. This was something that was noticed also in the case of the skin, as you can see here. In any case, like ab initio calculations arrive up to let's say a certain point. So they are more concentrated, let's say, on low values of L. So that's definitely something that that enters here. So I could stretch, I could zoom in this picture. And also, like, if I remove, let's say, the ab initio calculation, actually, it's pretty good from the EDF side. But still, like, it's there also for the ab initio calculation, they're just more compressed.
I see.
Yeah. Yes.
When they started looking at this correlation here, they didn't put J. It was only alpha sub D versus L, okay? Is okay? When they started looking at this correlation, they use alpha sub D versus L. And then these guys from Spain and Milano, in these papers, they realized that if you multiply alpha D times J, the correlation is much better. And I think are those white triangles there. But it's not as good as the skin versus L. They gave some justification based on the liquid drop model, why you have to multiply by J to get a better correlation. But you are right, this doesn't look like it will solve the problem when we get alpha D and compare with data to obtain L, we will have a larger spread than with the skin. I'm sorry, I'm taking your time, so sorry.
Yes.
I thought I understood you to be saying that the scale here is only 25% from 6 to 8, where the scale over here is like essentially a factor of 2. So, while these look more scattered, if I think about it as a fractional uncertainty, maybe it's not really more scattered. Is that what you were saying?
Yeah, like I wanted to comment on the fact that like the ab initio calculations were lower, like we're indicating like lower values. That's
Okay, but I mean, in the end, I guess what matters is, the figure of merit is how well I can measure this combined with the spread of the correlation, because what I really want to know is how well I can infer L when I'm done, right? So have you done that? Do you have?
No, I haven't actually used the correlation itself. Like my way of looking at this, like there are actually two approaches, also like in energy density functional theory, they explore the two ways. They actually use the correlation, as you say, or they just said, okay, we just consider energy density functionals which are able to reproduce a certain set of data which we think are sensitive to the neutron to proton asymmetry, and we get constraints from that. And I just went with the second way.
Okay, very good. I think we can continue this discussion on this topic in the afternoon. So let's thank Francesca again, all the speakers of the morning. And then we try to